it blows, it could destroy the United States as we know it.
Dr. Michio Kaku sounds the alarm. Yellowstone is trembling. With hundreds of earthquakes now rocking the area, a terrifying eruption unfolds. As we delve deeper, Kaku's insights help navigate the magnitude of this natural phenomenon. The Earth awakens. Let's find out why. Yellowstone's allure is undeniable. From the Grand Canyon's majestic expanse, sculpted by the Yellowstone River, to the mesmerizing lower falls that cascade twice the height of Niagara Falls, the park offers unparalleled natural beauty. The Mammoth Hot Springs, with their unique combination of heat, water, minerals, and limestone, and the geothermal wonders of the Upper Geyser Basin, home to the legendary Old Faithful Geyser, are a testament to the park's geothermal activity. But this beauty is a double-edged sword, for beneath its serene beauty lies a ticking time bomb. The announcement by Michio Kaku that Yellowstone is on the brink of eruption in 2023 is nothing short of alarming. Such an eruption, categorized as a maximum eruption or Category 8, has the potential to tear the guts out of the United States of America. But why is this an alarming situation? Why should we worry? One of the most telling signs of potential volcanic activity is the uplift or subsidence of the ground. In recent years, areas around Yellowstone have experienced noticeable uplift, indicating that magma is moving closer to the surface. This deformation can be detected using GPS instruments that measure even minute changes in the ground's position. Yellowstone's connection to volcanoes is deep-rooted. The park's geothermal features, from geysers to hot springs, are powered by a fiery force beneath the Earth's crust. Recent studies have revealed that Yellowstone is recharging, meaning its magma chambers are filling up. Once filled, an eruption becomes imminent. The potential eruption could release up to 240 cubic miles of explosive volcanic rock, powerful enough to break through the Earth's crust. Recent events have heightened concerns. A colossal crack, a staggering 100 feet wide, appeared seemingly out of nowhere in Teton, prompting park authorities to close off a significant section for urgent investigations. The Tetons, known for their hard, tough rocks, are not strangers to the forces of nature. Over time, even the toughest rocks succumb to nature's relentless forces, leading to cracks and fissures. The discovery of this fissure in an area known for its geological stability is a stark reminder of nature's unpredictability. Embark with us on a journey to discover more events that have led scientists to make these shocking claims. Earthquakes are common in volcanic regions, but a sudden increase in their frequency or intensity can be a cause for concern. The area around Yellowstone has witnessed a surge in seismic activity, with over 121 earthquakes recorded in a single month. While most of these are minor, their frequency and clustering can be indicative of magma movement. Seismic activity, or the movement and vibrations within the Earth's crust, plays a pivotal role in the processes leading up to volcanic eruptions. Understanding this relationship is crucial for predicting volcanic activity and ensuring the safety of communities living near volcanoes. At the heart of every volcano is a magma chamber, a reservoir of molten rock. As magma rises from the mantle towards the Earth's crust, it can cause the surrounding rocks to crack and fracture. This movement of magma and the fracturing of rocks generate earthquakes, known as volcanic or volcanotectonic earthquakes. As magma accumulates in a chamber, it exerts pressure on the surrounding rocks. When the pressure exceeds the strength of the rocks, it can cause them to fracture, leading to seismic activity. These fractures can create pathways for the magma to travel, potentially leading to an eruption. Unlike typical earthquakes, which are short-lived and can be likened to sudden jolts, harmonic tremors are continuous seismic signals. They are often associated with the movement of magma and fluid within a volcano. The presence of harmonic tremors can be a strong indicator that an eruption is imminent. Sometimes a volcano can experience a seismic swarm, which is a series of earthquakes occurring in a short span of time in a localized area. While not all seismic swarms lead to eruptions, they can be indicative of significant magma movement or changes within a volcanic system. In essence, seismic activity is both a precursor and a consequence of volcanic processes. By closely monitoring seismic events, scientists can gain insights into the behavior of magma beneath a volcano, helping them predict potential eruptions and mitigate their impacts. Beware! There are more warning signs coming your way. Yellowstone's geysers, hot springs, and other geothermal features are directly linked to the underlying magma chamber. Any significant change in their behavior can be a sign of changes below the surface. For instance, the Steamboat Geyser's record-breaking 32 eruptions in a year and the sudden eruption of the previously dormant Excelsior Geyser are unusual patterns that warrant attention. The primary source of geothermal energy in a volcano is the magma chamber. As magma rises closer to the surface, it transfers heat to the surrounding rocks and groundwater. This heat transfer can lead to an increase in ground temperature, making areas around the volcano noticeably warmer. When groundwater is heated by the magma chamber, it can lead to the formation of hydrothermal systems. These systems consist of circulating hot water and steam, which can manifest on the surface as hot springs, geysers, fumaroles, and mud pots. The presence and activity level of these features can indicate changes in the underlying magma system. The influx of magma and the expansion of hydrothermal systems can cause the ground to swell, a phenomenon known as ground inflation. Conversely, when magma retreats or is expelled during an eruption, the ground can deflate. Monitoring ground deformation can help gauge the pressure within the magma chamber and the potential for eruptive activity. The intense heat and chemically reactive fluids in hydrothermal systems can alter the mineral composition of rocks, a process known as hydrothermal alteration. This can weaken the rocks, making them more susceptible to landslides and collapse. Satellite and aerial thermal imaging can detect heat anomalies on a volcano's surface. These anomalies can be due to fresh lava flows, a new magma intrusion, or changes in the hydrothermal system. Persistent or increasing thermal anomalies can be precursors to eruptive events. In some regions, the geothermal energy of volcanoes is harnessed for electricity generation. While this provides a renewable energy source, it's essential to monitor the volcano closely, as changes in the geothermal system can impact both the energy production and the volcano's behavior. Volcanoes emit a range of gases, including sulfur dioxide, carbon dioxide, and water vapor. A sudden increase in the emission of these gases, especially sulfur dioxide, can be a sign of an impending eruption. Monitoring stations around Yellowstone continuously sample and analyze these gases to detect any unusual spikes. Don't let the temperature drop, because we are just about to discover the impact of temperature changes on volcanic eruptions. The temperature of Yellowstone's geothermal features can provide insights into the magma's proximity to the surface. Any sudden or significant increase in temperature can be a warning sign. The viscosity or stickiness of magma is closely related to its temperature. Hotter magma is generally less viscous, allowing it to flow more easily, while cooler magma is thicker and more resistant to movement. Less viscous magma can rise more rapidly through the Earth's crust, increasing the potential for an eruption. As magma cools, it begins to crystallize. The formation of these crystals can change the composition of the remaining liquid magma, making it more volatile and potentially leading to explosive eruptions. This process, known as fractional crystallization, can segregate different minerals and concentrate certain gases in the magma. The solubility of gases in magma is temperature-dependent. In magma is temperature-dependent. At higher temperatures, more gas can be dissolved in magma. However, as magma rises and cools, these gases come out of solution, forming bubbles. The accumulation and expansion of these gas bubbles can drive an eruption. Hotter magma can burn its way through cooler surrounding rock, a process known as thermal erosion. This can create new pathways for magma to ascend to the surface, increasing the likelihood of an eruption. If external water from a nearby lake, ocean, or groundwater comes into contact with hot magma, it can flash to steam, expanding rapidly. This sudden expansion can contribute to phreatomagmatic eruptions, which are particularly explosive due to the rapid vaporization of water. While not a scientific measure, there have been anecdotal reports of animals sensing volcanic or seismic activity before humans. Any unusual animal behavior, such as mass migrations or erratic patterns, might be considered an early warning sign, though it's essential to approach such observations with caution. The intricate relationship between animal behavior and impending natural disasters has been a subject of fascination and study for many years. While it's not definitive, there have been numerous accounts worldwide of animals acting unusually before earthquakes, tsunamis, and even volcanic eruptions. Yellowstone National Park, with its rich biodiversity and the looming presence of the Yellowstone caldera, provides a unique setting to observe and study these phenomena. Many animals, especially those that dwell on or within the ground like snakes, rodents, and insects, are highly sensitive to ground vibrations. Seismic activity, which often precedes volcanic eruptions, can be detected by these creatures long before humans notice. Their heightened sensitivity might lead them to evacuate their burrows or display agitated behavior. Before an eruption, there can be an increased release of volcanic gases, such as sulfur dioxide. Animals with a keen sense of smell, like wolves, bears, or elk, might detect these changes in air quality and become restless or migrate to areas with cleaner air. The geothermal changes associated with an impending eruption can lead to the release of minerals and gases into water sources. Animals that rely on these water sources, like birds or aquatic life, might be seen leaving the area or even dying off in large numbers if the contamination is severe. If larger mammals like bison, elk, or deer sense danger due to changes in the environment, they might alter their migration patterns, moving away from the volcanic epicenter. Observing such shifts can provide clues about changes in the park's geothermal activity. Birds often have a broader perspective of the landscape and can quickly move to safer areas. A sudden and unseasonal departure of birds from certain regions of the park might indicate something amiss. If prey animals are agitated or moving out of an area due to seismic activity, predators might become more active or aggressive as their regular food sources become scarce. While anecdotal evidence abounds, systematic research on animal behavior as a precursor to volcanic activity is still in its infancy. Yellowstone, given its extensive monitoring systems and research facilities, provides an excellent opportunity to study these patterns in more detail. By studying the history of Yellowstone's eruptions and geothermal activity, scientists can identify patterns or cycles that might give clues about future eruptions. While the supervolcano's behavior isn't strictly cyclical, understanding its past can provide valuable context for current observations. The love-hate relationship between Yellowstone and geology can be explained by the Yellowstone hotspot. Keep up with us as we further dissect their story. The Yellowstone hotspot, a geologic phenomenon, has shaped the northwestern United States landscape for millions of years. Originating from a mantle plume, a column of exceptionally hot rock rising from deep within the earth, the hotspot has left a trail of volcanic activity as the North American tectonic plate moves across it. This hotspot fuels Yellowstone's magma chamber, providing the energy for volcanic eruptions and the park's geothermal features. Snake River Plain and the moving North American plate. The most evident sign of the Yellowstone hotspot's trail is the Snake River Plain, a swath of volcanic terrain that stretches from present-day Yellowstone in Wyoming to Oregon. This plain was formed as the North American plate moved southwest over the stationary hotspot. As the plate moved, successive volcanic eruptions occurred, leaving behind a trail of calderas and lava fields. One of the most destructive manifestations of the Yellowstone hotspot is the formation of calderas. These are vast, bowl-shaped depressions formed when a massive eruption empties a magma chamber, causing the ground above to collapse. The Yellowstone region has experienced at least 3 of these super eruptions, with the most recent forming the Yellowstone caldera approximately 640,000 years ago. Apart from explosive eruptions, the hotspot has also produced extensive basaltic lava flows, especially in the earlier stages of its history. These flows have covered vast areas, creating the relatively flat landscape of the Snake River Plain. Have you wondered what would happen if these eruptions take place according to predictions? Let's find out. The immediate vicinity of the eruption would experience catastrophic devastation. Everything within a radius of tens to possibly hundreds of miles could be obliterated, depending on the eruption's magnitude. The ground zero of the eruption, encompassing the immediate vicinity of Yellowstone, would witness an apocalyptic scene. The explosive force of the eruption would be equivalent to multiple nuclear bombs detonating simultaneously. One of the most deadly aspects of volcanic eruptions is the pyroclastic flow, a fast-moving current of hot gas and volcanic matter. These flows can move at speeds of up to 700 kilometers per h, 450 miles per hour, and can reach temperatures of about 1,000 degrees Celsius, 1,830 degrees Fahrenheit. Anything in the path of a pyroclastic flow would be instantly incinerated. The range of these flows depends on the eruption's magnitude, but they could potentially cover a vast area around the volcano. While not as rapid as pyroclastic flows, lava flows from the eruption would slowly and inexorably cover vast areas, incinerating forests, flowing over landscapes, and reshaping the topography. These molten rivers would render areas uninhabitable for years, if not decades. The intense heat and melting snow and ice can lead to lahars, volcanic mudflows that can move at great speeds. These mudflows can bury valleys, destroy bridges, and pose significant threats to areas even quite distant from the eruption's epicenter. One of the most widespread effects would be the ash fall. A super eruption from Yellowstone could produce an ash column that rises high into the atmosphere. Prevailing winds would carry this ash across vast distances. Depending on the eruption's magnitude and duration, ash could potentially fall over most of the United States, affecting areas from the west coast to the east coast and from Canada to Mexico. The ash, which consists of tiny shards of volcanic glass and pulverized rock, would smother crops, rendering vast agricultural lands unproductive. This could lead to food shortages, not just in the US, but potentially worldwide due to the disruption of one of the world's primary breadbaskets. Ashfall can contaminate water sources, making them unsafe for consumption. This could lead to a crisis in potable water availability in affected areas. Roads, highways, and airports could be buried or rendered unusable due to ash accumulation. This would disrupt transportation networks, halting the movement of goods and people. The fine ash particles can also damage vehicle engines and jet turbines, posing risks to any operational transportation. Inhalation of fine ash particles can lead to respiratory problems. The ash can irritate the lungs, eyes, and skin, posing health risks, especially to vulnerable populations. Whoa, that's not it. Continue with us to face the bitter truth. There would be real climate changes. One of the most significant global impacts of a Yellowstone supereruption would be the introduction of vast amounts of volcanic ash and sulfur dioxide, SO2, into the stratosphere. These particles can reflect sunlight away from the Earth, leading to a phenomenon known as a volcanic winter. This could result in a drop in global temperatures for several years, if not decades. The cooling effect could disrupt monsoon patterns, especially in Asia. This would have dire consequences for regions that rely heavily on monsoon rains for agriculture, potentially leading to widespread crop failures and famine. Cooler temperatures could affect ocean currents, which play a crucial role in regulating the Earth's climate. Disruptions in these currents could lead to unpredictable weather patterns and impact marine ecosystems, affecting fish populations and other marine life. Prolonged cooler temperatures would impact ecosystems globally. Many plant species, especially those in temperature-sensitive regions, might struggle to survive. Animal species, particularly those that rely on specific plants or other animals, could face extinction or migration challenges. While the immediate aftermath would be cooling, the longer-term effects on polar ice could be paradoxical. Volcanic ash settling on ice sheets, especially in the Arctic and Antarctic, would darken the ice, making it more susceptible to melting when normal temperatures resume. This could contribute to rising sea levels. Millions of people might be displaced from their homes, leading to one of the most significant refugee crises in history. This would put immense strain on areas unaffected by the eruption, leading to potential social and political tensions. Beyond the physical implications, the eruption would have a profound impact on the collective psyche. The loss of iconic landscapes, combined with the widespread devastation, could lead to a period of mourning and reflection on our relationship with the planet. Let's not forget the economic implications of such an eruption. The ash cloud from the eruption could severely disrupt air travel, not just in North America, but potentially worldwide. This would have a cascading effect on global trade, especially for industries reliant on air freight. The U.S. is a significant producer of oil and natural gas. Disruptions in production due to ashfall and infrastructure damage could lead to energy shortages and price volatility in global markets. The uncertainty and immediate impacts of the eruption would likely lead to significant stock market crashes and economic downturns. Given the interconnectedness of today's global economy, a recession in the U.S. could easily lead to a global economic crisis. The areas most affected by the eruption and its aftermath might become uninhabitable, leading to a massive migration of people. This could strain resources in areas receiving these migrants and lead to geopolitical tensions. The eruption would result in unprecedented insurance claims due to property damage, business interruptions, and other losses. The real estate market in affected areas would collapse, with properties becoming worthless. Thanks for joining us. Don't miss the video on your screen. It's a must-watch.